Okay, hello everyone. Welcome to the astronomy department of IAG, and thank you all for participating of this seminar. And today we are very honored to welcome Professor Katerina Whitaker from the University of Massachusetts at Amherst in US. Katerina, has a brilliant path in research, scientific research. She got her bachelor degree also in Massachusetts, right, Catherine? And in 2012, she got her PhD from the Yale University. And she's not only professor at the University of Massachusetts, but she's also associate faculty at the Cosmic Dawn Center in Copenhagen, in Denmark. Her research focused primarily on galaxy formation and evolution. And first, Catherine, thank you a lot for accepting our invitation, being here today with us, for sharing your research, your knowledge. And the talk of today from Catherine is Requiem for massive galaxies. I would like to tell everyone who wants to send questions via YouTube, you can also send via chat. And I will bring them to Catherine by the end of the presentation. And unless Catherine says otherwise, we make questions by the end of the presentation. And I will ask all my colleagues following the seminar via Google Meet to please turn off the cameras and microphones. And Catherine, you feel free to start whenever you want.
Awesome. Thank you so much for the invitation. I'm very excited to join you remotely. It would be more fun if I were there, but nonetheless, I think we're going to have a good time together. And I'm excited to share with you my research in trying to understand the formation of the most massive galaxies and really this mystery of why these galaxies shut down their star formation so early in the universe. You'll see at the bottom here a link that we're going to put in the, Ronaldo, I'm hoping you can put it in the Google chat window. I just have one question. A little bit later, I saw that the lights in that room are dark, so just to make sure you're all awake. So stay tuned, that's later in the talk. But really, it's my pleasure to join you today and talk to you about a bunch of different programs we've been doing using world-class facilities like the Hubble Space Telescope, ALMA, and most recently the James Webb Space Telescope. So,
before starting, you need to please click on hide on that small text.
Whenever I do that, it makes my screen go away. Can you still see slides? Would you? I've tried that several times. Would you like me to? You probably can't see my presentation anymore, correct?
Yes. And now we cannot. And now we
Maybe
can.
that works.
Okay.
Okay. That works? Okay.
Yes.
Cool. Right. So, studying galaxy formation and evolution. So, really, the study of galaxies is understanding how we formed from a heterogeneous universe from a nearly homogeneous beginning. So galaxies form at the sites of these tiny quantum fluctuations in the aftermath of the Big Bang. And this, as these, in our framework of lambda cold dark matter cosmology, this tells us how these cold dark matter clusters and clumps together to form the galaxies that live within them. But really, it is understanding the physics of star formation, so how gas, that's the fuel of star formation, how does it flow into galaxies, how does it flow out of galaxies, and what is regulating star formation in these galaxies, especially in the early universe, that has been our main bottleneck of understanding this area of research. And so when I think of this, I'm an observational extragalactic astronomer, and so we go out and we take the deepest images that we can of the universe, and the trickiest thing is figuring out how, when we see a galaxy, what epoch of the universe are we exploring? So effectively, if we want to piece together a history of the formation of galaxies, we want to do this in a statistical sense. It turns out we can't watch galaxies over billions of years, so we can't watch a single galaxy unless you're a theorist and then you have magic powers. As an observer, I cannot do this, but what I can do is use the power of statistics and try to look at how the properties of galaxies have evolved from the early universe and looking at snapshots of our universe and how they evolve into the present day. So one of my favorite images of the cosmos is shown here. This is the Hubble Deep Field. This was taken in December of 1995. And this was really a turning point, I think, for extragalactic astronomy in terms of how resources were allocated. And at the time, it was really ambitious. Astronomers at the Space Science Telescope Institute used director's discretionary time to point at a tiny region of the sky for 10 consecutive nights. So it would be the equivalent of taking a grain of rice at arm's length, and that's how small of a patch of the sky they were looking at. And this is the really remarkable image that came out, and you can see a broad diversity of each of the objects in here, for the most part, are galaxies, with the exception of a few foreground stars. So you can see here's a star in our Milky Way, here's another star. By eye, I can pick out 3. But if you look at these other galaxies, they have a wide range of colors. Some are brighter, some are bigger. And so really, taking an image like this, the hard part is then saying, okay, well, how far away are these galaxies? How long has that light been traveling to us? And therefore, how far back in time are we looking in the universe? And in this image, we captured some of the most distant galaxies we've ever observed. And so it's with surveys like this, we had a changing point in terms of studying early galaxy formation and trying to understand that. So I mentioned this is one of my favorite images, and what's really striking is where we're at today and what's happened in the last year. So when this image was taken, admittedly, astronomy was not on my horizon. You can see here, this is an image, a cutout from my 5th grade yearbook, just before this image was taken, around the time they were making these decisions. And at that time, I thought by 2010 I would be a travel agent with a husband and children. And really, this was not at all on my mind. So I don't know that I necessarily paid as close attention at that point. But really, Hubble imaging has made my career. And most recently, with the launch of the James Webb Space Telescope in December of 2021, we've really entered into a new era. And at the end of my talk, I'll talk about some of the really recent results that we're finding, bleeding edge science of what we're doing with this new facility. But one of the first things that came down was this Webb Deep Field. This is last July. Many of you might recall. And so on the right is a picture of us I was watching with my family and with my children. My children are about the age I was when this Hubble Deep Field image was originally taken. The US president's briefing. So seeing these very first images and sharing them with the public through this press conference in July of last year. And really, now you see the Webb Deep Field here. This is the SMACS cluster, and you see this effect of strong gravitational lensing, which I'll talk about in my talk today, and how we can use this as a tool for understanding deep galaxies. But really, it's phenomenal. So if we just zoom in on this image, the level of detail we can see with this new facility is just remarkable. If you look at some of these galaxies and you see all these globular clusters and galaxies that are over 10 billion light years away from us, it's just a really remarkable new level of detail, and we can go much deeper. So really, I share all of this to motivate at the beginning of my talk that we're at a very exciting point for galaxy formation and evolution, and especially in pushing our understanding of galaxies towards cosmic dawn and really to the very first galaxies. So in this talk, what I wish I understood in my research and what I want to talk about today is how do the most massive galaxies form and what quenches their star formation. And so I mentioned at the beginning this framework of lambda cold dark matter and how structures of galaxies are dominated by the dark matter halos that they live in, but it's really that gas physics that's our bottleneck, and that's very tricky to couple and understand feedback in galaxies, understand what drives star formation and what ultimately shuts off star formation. These are big questions. It's great. It means I have a career and a long road ahead to try to understand them, but I'll break them down into what I think are more manageable questions. So specifically, what I'll talk to you about is the most massive galaxies and the shutdown of star formation. And so looking at when galaxies quench, what happens to their structures? That is primarily governed by the dark matter halos that they live in. And related, how well do we understand their stellar populations, the stars in these galaxies? And this I mean in a spatially resolved way. So what's happening in the very centers of these galaxies versus further out. And then finally, also trying to understand and get a reading on how much cold gas, which is the fuel of star formation, these dead galaxies have. And trying to understand if they're running on empty or if they have full gas tanks, but they just can't convert that gas into stars. So something is making them inefficient. So you can see here, just trying to understand the ecosystems of massive galaxies and how gas is expelled out of these galaxies, how it is possibly fueling rejuvenation, and how their metal enrichment histories evolve. On the left here, I'm showing you the greater ecosystem really zoomed out to a very big physical scale. But what I want to stress is, for the most part, from here on out, what I'm looking at are the very centers of these gravitational potential wells. So when we look with Hubble and with Webb, we're really seeing the starlight at the very center. And what's invisible to us is this bigger ecosystem. But we can look for clues in the data to try to understand what we're seeing. I'm showing here a schematic of a possible way of forming these early galaxies. So massive galaxies by nature, or I guess by what I'm selecting, have a lot of stars in them. So they form stars very rapidly, very early in the universe. And it's been known for over a decade now that these early massive galaxies are remarkably compact in size. And this has been an ongoing area of research of trying to understand, how do you form such compact galaxies and how do you quench them? And I'm showing you here possible schematic evolutionary picture of what we're looking at. So if I focus on the later half of the history of the universe, from the peak epoch of star formation over the last roughly 10 billion years, we see evidence, empirical evidence from observations, that these compact galaxies, we see that they exist early in the universe. And what we think is the minor mergers and accretion puff up their outer envelopes over time. And so that they evolve into present day, local, very massive elliptical galaxies. I'm showing you a plot here of the surface mass density as a function of radius, averaged out looking at really high redshift. This is work by Allison Hill, down to the nearby universe. So you can see here, the mass profiles are very compact, centrally concentrated in the early universe. And by the time we evolve, 12 billion years later, with this minor mergers and accretion, these galaxies are slowly, they have similar cores, but they're slowly puffing up their outskirts. And this sits together with our current framework in lambda cold dark matter cosmology. Now, I mentioned, okay, we see that there are compact galaxies, but it's really an open question in terms of how did these form, and how are we understanding this earlier branch of galaxy, the earliest branch of massive galaxy formation. So there's different ways that you can form such compact of a galaxy. It could be something like a monolithic collapse that happens very early in the history of the universe when everything is a lot smaller. And so you form a really dense, compact galaxy that lives in a relatively undisturbed dark matter halo, and that can evolve forward to be, a few billion years, and we observe it as a compact, often dead galaxy. And then these other two branches are ways where we're really driving gas to the center of these galaxies, and it's a late stage event that's happening just before they're quenching, where they have a big burst of star formation in terms of gas compaction that's driving violent disk instabilities, drive gas to the center of these galaxies. and you can have a big burst in the center and form a bunch of stars there, or the more classical gas-rich major merger picture, which has been around for decades in terms of merging two spiral galaxies that have a lot of gas and forming a compact remnant. So what I'd like to understand is what I'd like to do is look for clues to be able to pick out what formation pathway. That's sort of my end goal here. And next I want to segue into, okay, well, before we can understand all this, we have to first find distant galaxies and be able to identify those that have shut off their star formation. So one of the main tools commonly used for many years now is rest frame colors is used to separate out these galaxies in the distant universe. On the left here, I'm showing you work that's adapted from Mariska Creek's paper in 2011. These are composite spectral energy distributions. In blue, you're seeing a star-forming galaxy. You can see that this is a relatively blue galaxy with ongoing star formation, and that's this rest frame UV emission. You see a strong Balmer break, and it turns over. In comparison, I'm also showing you in purple and in red two different types of galaxies that we see. If you were to, for example, take that blue star-forming galaxy and maybe you see it face on, but maybe by chance projection, you see it through the line of on edge, so looking through the disk. When we look through big column densities of dust, that will attenuate the ultraviolet light. And so you see something like this purple SED, where dust has absorbed that UV radiation and it's radiating it at longer wavelengths than we're even showing here. Or it could be that galaxies are intrinsically red and dead. They have stopped star formation. They no longer have UV emission. And they're really dominated at that point by older, lower mass, longer lived stars. And so that's what you see in red. And so the color diagnostics are great because you can pinpoint for large samples and take advantage of the shapes of these SEDs to distinguish. So here, the UV, which is a rest optical color, rest frame, you can see that you can separate blue galaxies from red galaxies for sure, but it's really hard to distinguish between a red galaxy being inherently red and dead or vigorously forming stars, but just very dusty, which are two fundamentally very different types of galaxies, but morphologically they could look the same. And so this is where the rest frame J-band filter comes, where quiescent galaxies turn over faster than those that have dust attenuation and are very dusty and star forming. So we use this color diagram to identify candidate quiescent galaxies. This is what I'm showing you here. So this is that UV color as a function of the V minus J color. This is the star forming sequence along here. And you can see, I like showing this work from Shannon Patel because he has postage stamps of galaxies that fit into this different parameter space. And you can see very clearly you have blue galaxies down here, often face on spirals. And you see this effect of either edge on, so you start to see these galaxies through their disk, through a line of sight of dust, or some of them have mergers that just intrinsically have a lot of dust in them to obscure the ultraviolet radiation. But up here is where we see these red and dead, and they tend to separate out. That's seen a little bit better on the right-hand side, which is just showing you the number density and showing you that there is a bimodality to some degree in these populations. And so what we found was if you just focus on this quiescent population, where exactly galaxies live depends to first order and just on how old they are. So in this bottom left corner here, this is where you have recently quenched galaxies that have stars that are about 1 billion years old. They've recently shut down their star formation and joined this red and dead population. And then as you go up along this vector, on average, these are older, redder galaxies. So the stellar populations have shut down, that we think that shutdown is permanent and they're aging, and that's why they move along this vector. So this is all work that is, at this point, this was for my PhD thesis, so it's a decade ago. But I was really delighted to see that this trend was confirmed with a really huge effort led by Sirio Belli, getting spectroscopy, very deep spectroscopy of distant galaxies. And this is showing here his work of spectroscopically confirmed quiescent galaxies where he's age dating them. And again, we see almost too perfectly the same trend that we get from photometry, which is much cheaper to get than spectroscopic data. So why do I show you this? This is twofold. It's a really great tool if you want to understand what's quenching galaxies. It's important to be able to identify those galaxies that just shut off their star formation, the most recently quenched galaxies, and try to look for signatures that we can trace back to their formation relative to the older population that joined earlier in time relative. So, and the second reason is more recently, folks have been using these color diagrams to try to understand timescales of quenching and how galaxies evolve, the colors of galaxies evolve, and how they evolve in this diagram to see if we can use that again to understand their formation pathways. So this is work by Sirio also. And so what he has added on here, what I want to highlight, so this is again, oh, I've lost a label, but the y-axis is the U minus V color, and the x-axis here is again V minus J. This is the quiescent region up here, and he's highlighting a box he's calling post-starburst. Those are the recently quenched galaxies. And what he shows in his paper is these two pathways here. So you could have slow quenching if the process of shutting down star formation in these galaxies lasts for over a characteristic timescale on order of a billion years, then you will tend to enter this quiescent region through the side. On the other hand, if what is happening in these galaxies is abrupt, they very short timescales for quenching of order 100 megayears, they will evolve up through this post-starburst region here. And so this is interesting because we can pick galaxies in these different regions and model their star formation histories and try to understand and look and connect that back with other characteristics that they have to understand their formation. So using this, I wanted to share with you a study. This is led by Mo Akshik, who is my former PhD student. And Mo found this galaxy. And you can see here on the left is that same color diagram. And on the right, I'm showing you a similar one, but instead of U minus V, the lever arm is a little bit wider and we're going into the rest frame near UV. And so it's more sensitive. The right diagram is more sensitive to very recent star formation. If we put his galaxy on this diagram, and you can see in grayscale the parent population. So it's basically right in between. Would we say that it's a slow quenching galaxy? According to some of the tracks that I just showed you from Sirio Belli's work, it would be consistent with that. But if we look at the near UV, it's a little bit further down, like it's had some sort of recent burst. And so this is an interesting test case to try to understand what we're seeing. This is, if we take this data and we model its star formation history, model its global star formation history, we observe it at a redshift of 1.88. So this is roughly 11 billion years ago. But you can model back in time what we think happened to this galaxy based on how it formed its stars. And so the interesting thing here is that we think if you could have seen it just a little bit earlier, it was actually securely up in this quiescent region. And it actually entered in the more classic post-starburst rapid quenching scenario that I mentioned earlier, but has popped down. So what is going on here? So in this analysis, we're seeing some evidence that this galaxy has had some sort of a rejuvenation event. If we take it one step further and look at modeling the star formation history in the center versus what's happening in the outskirts, you can see that the center is shown in blue. And then just a kiloparsec out, this is a very compact galaxy, just outside of that, we're modeling the outer region. And so what we're finding is a central rejuvenation. So you see evidence that just in the center of this galaxy, something is happening and it's turned back on. The right-hand side, so what I didn't tell you is this galaxy is strong gravitationally lensed, and I'm going to get into what that means shortly. But you can see here a reconstruction where you see this little hint of blue just in the very center of this galaxy and otherwise a very red population. So I'm going to return to this case study, but I think it's a really interesting case where, you know, if you look at something at the surface, we look at globally what we think is happening, there's some ambiguity here in possible solutions, but by adding, in this case, we added GRISM spectroscopy and we did a spatially resolved analysis, you can see more, you can get more information about this galaxy's formation history. hopefully I have you all with me still. Why I mentioned that this, it's stuck on this page. Oh, we're here. I mentioned that this galaxy is compact and that it's strong gravitational lens. You can see it in the bottom corner. These two yellowish galaxies are two cluster galaxies that are lensing, and we see 4 images of the same galaxy shown in red. And wouldn't it be great if we could do this for all distant quenched galaxies? But this is really where we hit the limits of our technology to date. So shown here is the angular resolution of a bunch of telescopes. I should really turn JWST from a dashed line to a solid line because it is real, not imaginary. It is working, it is operational a million miles from Earth. But what you can see on here are the resolution limits. And then in orange is the half-light radius of these quiescent galaxies at redshift of 2, at the peak epoch of star formation. And we're really getting very close to the limit which our telescopes, these galaxies are just barely resolved. And so it's hard if you need to spatially resolve the stellar populations, but something is just barely resolved. You're really at the cusp of what's possible with current facilities. You can see on here, future 30-meter ground-based telescopes and or Keck in space type instruments really will change the playing field for this area. But until then, this is what we have. And so this is where strong gravitational lensing comes into play, and it's something that we've used in my research group. You can see on the right is an animation, not to scale, of how strong gravitational lensing works. So what we're leveraging are special lines of sight of galaxies that are behind nearby clusters of galaxies. So you find a big cluster of galaxies, you have a distant galaxy, and as the light from that distant galaxy is traveling to us along the line of sight that passes by this cluster, light, due to general relativity, is bent. The space-time is bent, and so you have galaxies appear, as you can see here, stretched as giant arcs if they're in just the right configuration. They're much higher spatial resolution. They're a lot bigger on the sky, and they're much brighter at all wavelengths. And so this is great if you're trying to study distant early galaxies that are very faint at the limit of technology. Any boost you can get is amazing. On the left is one of our poster childs for the Requiem survey here. And it's this, you can see these multiple images of the same galaxy, and it's lensed by this foreground cluster that you see in yellow. Really a remarkably bright lens that was discovered by Drew Newman. So Requiem is a survey that stands for Resolving Quiescent Magnified Galaxies. You can see the URL here. And this is really a big team effort. These are strong lensed quiescent red and dead galaxies from a redshift of 1.6 out to a redshift of 3.2. So within the universe was about 2 to 4 billion years old at this point. And this is you get what you get and you don't get upset type sample. So it's a decade of effort of trying to find galaxies. Red and dead galaxies are rare by nature anyways. And so to find them also in the right configuration to be strong gravitationally lensed is even more rare. So these are really gems that can do next generation science now, but just for a very limited small number. On the top, you see what these galaxies look like on the sky. And on the bottom is what we've reconstructed, what we think they look like if you were to take away the distortion that happens with strong gravitational lensing and reconstruct what the light looks like before it's been passed by this cluster. And so again, I wanted to highlight some work that's led by Moak Sheikh. This is through his PhD with this survey. But first, I wanted to take your pulse and with this poll. So it'll load if you go to pollev.com/kwhitaker400. I'll have a series of questions. Hopefully it's in the chat window and it'll show up on the next slide also. But I encourage you to take out your phones or your computers at this point and play with me. And so what I wanted to ask you is, what cool things are we discovering with Requiem? Is it that A, quiescent galaxies aren't actually dead? B, that we're finding new multiple image sources that can improve our lens models, which always helps in terms of those reconstructions. C, quiescent galaxies quench insanely early. Or D, supernova, exploding star. Oh, and it's working. Great. Can you guys confirm if you see, I leave at least one vote of quiescent galaxies aren't actually dead. Not dead yet. Do you see the results, or is it just me? I hope it's you too. Give it a moment. I'm hoping either everybody up. Okay, we have at least another vote. Come on, you can do it. Pick up your phone. Share with me what you're thinking. This is one of my favorite things about polls. I can't see you, but I can like get inside your brain and discuss this a little bit, see how it changes live. Do you get influenced by your peers, what they vote? Does that change how you vote? Okay, I'll give you a few more seconds. Oh, we're changing again. We still got votes coming. Okay, we have a lot of enthusiasts for lens models. It's important to build a good lens model. That's how you make sense of reconstructing these galaxies. So strong gravitational lensing is an amazing tool for a limited number of galaxies, but it is complex. Oh, we've switched. The tides have turned. People just really want dead galaxies to not be dead. Awesome. I see nobody wants a supernova. Usually if I say that, maybe it'll change. Yeah, there you go. Perfect. Well, this is a lovely half Gaussian distribution. So I'm going to pause here. Nope, people are like not dead yet. Still great. So this is sort of a cautionary tale in terms of, I mentioned at the beginning, we have all this amazing web data, and similarly with Requiem, using space telescope data is such a privilege. And one of the things when you have this data is always trying to be open to new discoveries and new parameter space and things that we just didn't know before. And so we like to think about discovering the unknown unknowns as you're looking at data and being open to that. So taking a very brief diversion, we actually did discover a supernova in our data. So you can see here, this is a screenshot. This is no longer what my whiteboard looks like in my office. Now it's covered with James Webb Space Telescope notes and everything. But for Requiem, I had in the bottom, crazy science, a supernova discovery. And around this time, a couple of years earlier, was, for reference, this discovery of a multiply image supernova Refstel, in one of the frontier fields. So not to say that it's totally crazy, but it's just one of those things that's unpredictable. So shown on the right here are the two epochs of observation for our poster child, MRG M0138, first discovered by Drew Newman. So Drew took observations with Hubble in July of 2016, and through Requiem, we came back 3 years later in July of 2019 to get more data. And so what you'll notice is there is this object that appears within this galaxy. And I should move on so you don't see all my bad notes on my board, and you can actually see the image of where these are located, of this transient source in this galaxy. So we see it in all three images. You can see here, supernova here, here, and here. And what you might notice immediately by eye is the color of the supernova is different. And this is because we have long time delay with cluster lensing. And so the amount of time it takes the light to reach from supernova image 1, the supernova explodes, right, at the same time, but the light takes a different amount of time to reach us. And so this is why strong lensing is a really powerful tool if you do have a transient event like this, because it constrains cosmology and can be really important for firming up our cosmological models and understanding what sort of the basic makeup of our universe. So what you can see here is that when we came back, it was no longer there. This is confirmation that it was a transient event, and we went back and analyzed the earlier data. What is really exciting, and especially for the young folks in the room, is, drum roll, don't hold your breath, but there is going to be a fourth image that will appear up here in this image, and we predict that to happen in 2037. And this is why we call this the supernova Requiem, done only because of the survey, but also because this is around the time that Hubble is scheduled to be decommissioned and crashed intentionally into the ocean. And so Hubble discovered this supernova. And so it's a nice tribute. Another interesting thing about the supernova is that it's likely to be a supernova 1A. So these are a white dwarf that is accreting from a neighbor and has reached the Chandrasekhar limit and explode as a standard candle. And so stay tuned. If you're not busy in 2037 plus or minus 2 years, you could monitor this and see the reappearance of Requiem, supernova Requiem. So back to our regular program, you guys were excited that quiescent galaxies aren't actually dead. You know, that is entirely viable, certainly in different regions of these galaxies. So let me tell you a little bit about this survey. I should go a little bit faster. So what we've been using is GRISM spectroscopy in Requiem, and this is led again by Mo. And so you can see on the left is the full data set, and the GRISM is you have the light coming from your source. It goes into Hubble, and there's a grating on top of a prism. And so the incoming light is spread out by wavelength. What that means is for every image in the field of view, you get a spectrum, and it basically separates out, an image at red wavelength or blue wavelengths rather, and then you see images, overlapping images, a low resolution spectrum as a function of wavelength. And that's what you're seeing in the top left corner. It's amazing because you get a spectrum for everything in the field of view, but it's really tricky data because you get a spectrum for everything in the field of view. And there's a lot of contamination and overlapping light that needs to be modeled out to be able to extract science. And that's what this middle frame here is in terms of developing a contamination model to really just separate out the source that you are interested in. In this case, this is that galaxy I showed at the beginning that has central rejuvenation. And so Mo developed an entire framework, which is now publicly available, called Requiem 2D. It's available on GitHub, which is a joint Bayesian analysis of the GRISM and HST imaging, where we're using both combining the spectroscopic and photometric data, including star formation history priors and a dust and metallicity uncertainty is folded into this, as well as some nuisance parameters. So in this case of this example here, you can see in the source plane reconstruction, effectively what we're sampling on sky with the GRISM with these little dots sort of slicing across this galaxy. And indeed, you see evidence in the GRISM for this enhancement in the center, a very recent central burst of star formation only happening in the center of this galaxy. Requiem 2D is a public code. It is generally applicable. Mo ran a series of tests on Illustris. And so you can see on the right-hand side, here are the actual star formation histories of galaxies in Illustris. And next to that is what Mo recovers from a spatially resolved analysis, as well as a global analysis for these galaxies. So seeing if we can recover gradients in stellar populations, as well as just robustly modeling the star formation histories of these galaxies overall. So I encourage you to check out Requiem 2D, and the URL is at the top. So what Mo wanted to do with our Requiem galaxies is look at coming back to this idea of quenching timescales and formation and how these galaxies are forming. On the Y, I'm going to walk you through what this plot is. The Y-axis is the timescale, quenching timescale here. So if you, sorry, let me back up. Let me start with the X-axis. The X-axis is the global formation timescale, and it's normalized at the epoch of observation. And so you can see where about half of the stars formed. And so in this example, they formed earlier. So most of the star formation is earlier. This is the present day. This is past. They formed earlier. Whereas this galaxy formed more stars closer to the present day. And so you see a little shift here. And so early formation, late formation. The Y-axis is then looking at the quenching timescale. So how quickly does this star formation taper off in its star formation history? Up here is slow quenching. So it's a longer timescale. And this is defined in a paper led by Adam Carnell. And then down here would be fast quenching, so a very rapid shutdown from in recent time. And so we're going to put Mo's galaxies on here. And the one thing we're adding to this picture that's new and unique to Requiem is that we can look specifically at the central quenching timescale. So what's happening in the center of these galaxies relative to their global formation. So let's see what we find. So we find a couple of examples of galaxies that form early, slow, and uniform growth in their inner cores. This one here is that poster child that hosts a supernova. You don't see two lines because they're exactly on top of each other, where the inner and the outer regions have very similar star formation histories, very uniform growth. This is an example where you do start to see, this is the global star formation history, and this is the central star formation history. And so you start to see some differences between these, but both of them have a relatively long time scale. On the exact opposite extreme, some of our galaxies have, they form quite late, so close to the epoch of observation. Most of their stars have formed and they quench very rapidly. That turnover is much quicker. You can see that here. And then there's a couple in between. And so you can see some also in between that have interesting, what's happening globally is actually not necessarily what's happening at the center of these galaxies. So the fact that we see this trend, and I'm boldly drawing a line by eye through very few data points, is quite interesting because it is opposite to the canonical picture that we've had in our mind where more massive galaxies formed faster earlier, which is not really exactly what we're seeing here. We're seeing something more complex happening in these galaxies. So stay tuned. We're hoping eventually that we can get some ALMA IFU higher resolution spectroscopy of these galaxies to understand more in terms of radial gradients, but also their metallicity and what's happening with their chemical enrichment histories. I wanted to shift gears, and we started a little late, but I'm really at time. Okay, I got to go fast through this and talk about their cold gas. And so this is showing the number density of evolution. I only show this because I wanted to highlight looking at Redshift 2 is a very interesting time because this is showing the number density of recently quenched galaxies in blue relative to the older population. Most massive galaxies formed and quenched by Redshift 2. The population is mostly in place by Redshift 2 and then evolves very little. And so if you want to understand what's happening, we need to look towards earlier times. Now, this is the state of the field at earlier times in terms of looking at how much cold gas, the fuel of star formation, these galaxies have. So looking at high redshift, and this is a compilation. This is the dust fraction. And if you assume a gas to dust ratio over here, you can get molecular gas fraction. And this is where the state of the field at high redshift. Galaxies have a lot of gas. That's your takeaway here. If we then consider quiescent galaxies, you can extrapolate these scaling relations and make predictions as galaxies fall below the star formation sequence as their star formation shuts off. And you see these predictions from stacking here. And so what we wanted to do is go and use strong lensing coupled with ALMA to try to see if we can make measurements for these Requiem galaxies. So this unexplored parameter space, and in particular, very low specific star formation rate, where you really want to couple that with the boost from strong lensing. So these are our HST images of the ones where we got ALMA data, and you can see the ALMA is the contours on top. And so what you'll notice is we have detections in 2 of our galaxies, and then these 4 are all upper limits, despite having very deep observations. If I put those onto this plot, these are the points down here, and we see something that's really interesting. These are the stacks. So this is also stacking dust. So using the same methodology, albeit this is much higher resolution dust imaging, and this is lower resolution. And so we see it's a very small sample, but there's a order of magnitude tension here, where our data at face value says that quenched galaxies have extremely little dust and by proxy, very little cold molecular gas, AKA they're running on empty. But stacks of statistical samples say, no, they're not on average. They have some dust and therefore some gas. It's still there. So what gives? I just wanted to highlight, and I'm not going to be able to go into this in any level of detail because I'm egregiously over what I wanted to say. It could be that we're making an assumption about the molecular gas to dust ratio. And we look in simulations and find this is a log scale down here, and it's the ratio of how much cold gas there is to dust. Dust is what we directly probe, and then we assume a conversion. Simulations predict that this conversion that we're assuming, which is right here, this dashed line, is very, very wrong when you look at dead galaxies, and that their dust is destroyed much faster than their cold gas is depleted. And so this is very interesting, has interesting predictions. It's something I want to look at with Toltec. And so these are, I'm going to actually just skip through this, but something I want to look at with Toltec. I think it'll be exciting. Okay, in my last minute, I wanted to mention Webb. I'm super excited about Webb. I'm so excited that I strongly convinced 2 of my children as a family for us to dress up as astronomy themed in October of 2021. you can see in the middle here, this is a sweatshirt my son was wearing, and on the back, he was the James Webb Space Telescope, and he had missions. And so we went and educated the neighborhood about this future mission that was launching only a couple of months later. So super excited for everyone to hear and learn about Webb. I'm involved in a bunch of large surveys. The one I've spent most of my time is with Uncover. I showed you SMACS at the beginning. This is that cluster at the beginning. Uncover, similarly, is a really unique cluster. It's sometimes called Pandora's cluster because it's not just one cluster. You can see 3 clusters merging together here. So it's a really rich cluster, and it's just really beautiful. They have NASA released a zoomable image, and it's just phenomenal to look at. This is work led by my group at UMass. John Weaver is a postdoc, working also with Sam Cutler, who's a graduate student, and Richard Pan is a graduate student at Tufts, making and releasing publicly a catalog of this. This is all publicly available. I encourage you to go play with this data, read John's paper, learn about what decisions we've made. But a big effort for us was making this publicly available rapidly. It's a Treasury program, so you all can do science with it. And that's what we've prioritized. We're searching for early quiescent candidates. We find some promising ones in this field of view. One of the most exciting things about Uncover is we had, it's one of the deepest programs in cycle 1, the deepest if you count the boost from strong lensing. And we get to go back in July and take spectra. And so we're right now picking out our targets. What are the most interesting things to go back, look at, and get spectrum of? And so you see in here, for example, a candidate quiescent galaxy at redshift 6.5. I hope we're going to put a slit on that galaxy, as well as some really phenomenal quenched galaxies still at really impressively high redshifts that have strong gravitational lensing. I apologize, I'm flying through this. It's just, all of this is very exciting. I don't know if you guys heard about this. This is sometimes marketed, this is work led by Ivo Labbe. These are sometimes marketed as the universe breakers. And so when that first image came down, one of the first things we noticed were some really red galaxies. And that's what's shown here on the left in red. These are really high redshift galaxies. And modeling their spectra with the current state of the art tells us that they're impossibly massive, impossibly early. And that's why they are called the universe breakers. Do I think we broke the universe? Absolutely not. Does this tell us we have so much to learn? Yes, we have a lot to learn about how galaxies are evolving and forming really early. And, you know, I know we're not getting some things right. So again, this is a great learning experience. These impossibly massive, impossibly early, you can see here, they're breaking. This is unallowed by our current cold dark matter cosmology. And these galaxies are right at the cusp of having almost 100% star formation efficiency to be that massive that early. And then the last thing I'll show is work by Jacqueline Antwi-Donso, who is following up some quiescent candidates at quite high redshift. You can see here confirmed redshift 3, 3.7, 4.6, and 4.9. So very early dead galaxies. And in particular, these last two, so these are their star formation histories. And in particular, these last two down here are consistent with these universe breakers. So I'm also showing you work by Adam Carnell of a redshift 4.6, beautiful spectrum that came from Webb that would be consistent if this quenched galaxy, if you saw it earlier in time, it would look like one of these universe breakers. So it's really interesting. This is sort of where we're at. It's very early stages. It's very exciting. Lots of ongoing research. I really encourage you to stay tuned or get involved. All of our data for Uncover is public, so you can use it. And I'm very egregiously over time, so I'm going to just leave I'm going to come back to mine. I wanted to thank my research group, awesome group at UMass, thank the collaborators that I get to work with, and then also thank you guys for listening. And I hope I can leave enough time for some questions and leave my slides up here. Thank you.
Thank you very much, Catherine. Let's thank Catherine. Thank you for the very interesting talk and for making it very clear and light for us. And now we open for questions.
I'm not sure if that was sarcastic or not.
Sorry?
So I'm not sure if that was sarcastic or not. There's a lot in there.
Okay. So we have here some questions from the auditorium or the rise. First, Camila.
Hi, thank you for the excellent presentation. I learned a lot. I was very intrigued by that supernova discovery that you guys made. And I was thinking, how do you guys classify that supernova? It was like by the light curve or the spectrum that you say it was a type 1A type supernova, right?
That's a great question, and I will also say I am not a supernova expert, but I do know what we did in the modeling analysis. It's strictly based on the color. So you have a lens model, and our lens model, to the best of our ability, tells us what we think the light paths are in terms of how long, and then we also have directly measured colors of that. And so you saw by eye when I showed you that image, they have different colors, the different images. I don't know if I don't know how far back it was. I don't know if this is worth it. I might get you can see all my slides in reverse. I think it was right here. Sorry, this one. And so you can see the probability of the different types of supernova based on how bright. These are the 3 different images. This is before you correct for magnification. So up here they're very bright, and then we correct for what they would be intrinsically. And so that's these points down here. And then this is the observed color just in 2 of the filters that we have. And it is, it's at, I think it was 80% probability of being consistent with type 1A supernova. It's not entirely inconsistent with 1B or 1C. You can see that over here for these. I think in this field of view, something that could help in terms of decreasing these uncertainties is first improving the lens model, and so getting more multiply. A lot of people voted for multiply imaged, new multiply imaged. So having like web imaging of this cluster, I think would really could improve the lens model. But it's really coming from this. Unfortunately, it happened in the past, so we can't take a spectrum.
Yeah.
Wish we could rewind time, but we do have the color information, and if you wait enough, there is a prediction of the 4th image. I wouldn't, stake my career on that, but.
Okay, thank you very much.
Yeah. And you can see the time delay, by the way, the color evolution. This is the model that predicts that these are as time is evolving, how the color is changing and the brightness relative to the model and then the points over here.
I myself I have some questions, some basic questions. First, these quiescent galaxies, are they typically in populated clusters, or there is some correlation between the environment for these quiescent galaxies?
That is such a great question. And I actually just this morning was on a science organizing committee meeting that was talking just about this, the environments. This is a tricky question that we really know very little about. So I hesitate to say, they're in overdense environments and this can relate. A lot of these are field galaxies. I would say we don't have a lot of information, robust information on their environments. One of our lensed galaxies that actually unfortunately is not in the HST sample but is in our bigger sample is in a known overdensity we discovered with ALMA. And so we went and we saw all these neighbors consistent with a similar redshift in the ALMA data. But I would say stay tuned, and I'm not sure lensing is the way forward, but one thing I'm really excited about is the prime focus spectrograph on the Subaru telescope is going to have spectroscopy for a square degree field of view. And from that, I think we can get the high resolution spectroscopic information we need over a sufficiently wide area to try to finally link environment of these quiescent galaxies and really fold in. That's something I want to do in the near term being like the next 5 years, is try to answer your question. So I don't have an answer. I guess I can come back in 5 years, maybe.
Great, thank you. And I have another question. When you showed, I think by 1/3 of your presentation, some diagrams, color, one using near UV. So you reconstructed the history of the star. Yes, this one. So in this calculation, I think you showed the model you are using, which is publicly available. Is it so that formation history, star formation history quotes?
Yeah, it was after, it was before the, no, it came after the, sorry. No, now you got to watch all the arrows, sorry.
Yeah. Yeah, my question is about these calculations, this going back in time for this, for example, this galaxy, this specific galaxy. So do these models take into account events of merger or interaction, or it's for a galaxy isolated?
So the way that we've adopted the star formation history is modeled in what's called a non-parametric star formation history. So we're not assuming, this indirectly answers your question. We're not assuming that it's a single burst tau model, for example, that has some parameterization that you can't deviate from. You have many time bins, and so you can allow, there is a star formation history prior that is a prior in the slope of this. So whatever happens, you're conserving the slope of the star formation history, but you can have bursts and you can have star formation turn on and turn off. And so indirectly answering your question, if, for example, you had a merger or an accretion event or something that happened, it's a little bit tricky, and I would argue you really want high resolution spectroscopy to try to be sensitive to that degree, where often the data that we have is really more of an average history, and so you kind of, in effect, you're averaging over what you recover. And you can probably see it best here. So like if you see some stochastic event, we're really smoothing over that. And that's because this is low resolution spectroscopy. And so when you make mock low resolution, but in principle, you could see things, we don't necessarily we don't make an assumption, I guess is what I'm trying to say. And so you could, it allows for things like rejuvenation. It allows for big bursts that are because you had a merger event. And those are things that are happening here, for example, in our test case with Illustris, where you can have, those things are happening, right? That's the framework of how these galaxies are evolving. And we broadly recover. So it's smoothed version of that, if you will.
I see. You said it's the minimum amount of assumptions you use to make it robust to this historic calculation, right? And I have a last question. For that specific case, you showed us that the center of the galaxy rejuvenates. Why is it so?
This is funny because I said at the beginning, I totally contradict myself. I said at the beginning, we think galaxies shut down and it's not common that they turn back on. And I stand by that. I think rejuvenation not common. I think the point we wanted to make was that it might be still uncommon, but that galaxies in their ecosystems, it's perhaps not surprising. It's surprising that they shut down and just stay shut down. And that's an interesting observation. So having things like rejuvenation, because these galaxies are embedded in a larger cosmic web, where they can have accretion events, and there's ample gas out there that could be accreted. We tried to statistically look at this, and there are predictions from simulations of saying how common. I think they vary quite widely. And the one point we wanted to make was, basically you'd miss this if you just looked at the global colors and you just measured the star formation history, which is really what most people are doing at this point. Moving towards spatially resolved analysis takes, especially at high redshift, where you need to look to understand quenching galaxies, because by low redshift, they're all dead, right? It happens earlier, so you need to look back in time. But having sufficient data to be able to look at that is rare. And so lensing is great because it gives us a tool to look at it for some, but it's not all galaxies. And I guess the cautionary tale is, maybe this is more common than we think, but not, at least if we trust simulations, and I think there's good reason to, it's not as common. And it could be, there are physical mechanisms that can stabilize gas, have hot halos, so you can't get cold gas down into the center to get these rejuvenations. We did look and follow up that galaxy with the large millimeter telescope when it was in early science operation. And we did not see any dust despite pretty deep observations. So it does seem to have not, if it did turn back on, it's not going to stay on for long. Doesn't seem to have a lot of gas in it. So maybe it's that's why we think it's about 1% of the mass. So it's not consistent with like a post-starburst, which is more than 8% in a big burst. This would be more of a frosting of star formation, if you will, which is actually quite common in nearby galaxies seen.
Thank you very much. More questions? If not more scientific questions, I would like to ask you, because I saw you are also involved in some outreach projects. We also have some outreach projects here. So we are also very interested in knowing what projects are you involved in, and what do you think, what's the importance for young scientists and graduate students to engage in this kind of activity?
This is such a big topic, and I would really welcome, I don't want to be the only voice here, so I would welcome other folks to chime in, but I can share some of the things that I've been thinking about. And there's sort of a wide range. A lot of the effort I've put is at our local level, but I think can be broadly applicable. We have, for example, at the secondary education level, we have a local program in an underserved community. It's one of the 40% of the community is below the poverty line, and it's not far from where we lived here in Amherst. And this program is trying to get girls, it's called Girls Inc., and they're trying to get girls into STEM. And the idea is that they go into the program in 8th grade and they see it through high school. And they get externships, they get exposed to, like, there's fun summer camps, lots of different programs, and it's multifaceted. And so one of the ways, this is a partnership with UMass generally, but in astronomy, I'm running a workshop where they're making their own false color images with Hubble and now Webb. Actually, the first workshop was a little bit stressful because it came 2 days after the Webb data was released. So I wasn't quite ready to give them Webb images yet, but I wanted to because they're so pretty. But in this, just trying to get these girls involved and and understand that they're very much capable and that it can be fun, and then just learning a little bit about it at a critical age in their turning point. We also are kicking off in our program something called Astro Troop. This is a faculty-wide initiative where we're, in our broader impacts, trying to get funding so that we can pay underrepresented minorities. So we have this thing in our department where we have underrepresented minorities. They're coming in, we see the numbers, but they're not lasting in our program. And so we want to change that. And research shows if you engage students, if you get them engaged and they can form their astronomy identity by doing research, that they might, well, hopefully we can help show that they belong. But it's not just that. The other parts of the program, so paid research during the academic year, but also we have funds to give them tutoring. So preparation can be an issue where, they didn't come into our program on the same level playing field. They didn't have the same resources as some other students with more privilege. And so making sure they have tutors and they have those resources. So we have funding for that. And then the third component is at our faculty level and at our department level, paying an external consultant for diversity, equity, and inclusion training. So just how can we be more supportive? How can we be inclusive? How can we understand different people's stories and what makes them who they are? And I think just having a deeper understanding of how to be a better mentor is so the program that we're trying now. And so we have, I just very fortunately got funding for the next 5 years for this program. So I'm super excited to keep this going in our department. And then the last thing I'll mention is RU internships. So trying to get, again, coming back to having an identity and getting as many people as we can doing research and getting their hands on data is really a high priority. So for me, it's through trying to send students to the Cosmic Dawn Center, so sending them abroad in the summer through an IRES, an International Research Experience program that I run. Unfortunately, it's NSF funded, so it's only for US citizens, which is kind of a bummer. But also just locally having internship summer. I'm the director of our 5-college astronomy department summer internship program of local students doing research. That is a broad range of things. I guess my theme is trying to get as many people supported doing research and help them form their identity, their research identity.
Thank you very much. It's wonderful to listen to your experience and to all these programs that you are involved to. And yeah, it's really interesting. We we also have some initiatives, and I think it's also important for us to listen other experiences and to, to get inspired also. And I will get some more information in your websites, and maybe I could get in touch to make some questions about this.
I'd love to hear what you guys, what you're doing. The thing I didn't mention was I also on my webpage try to make resources available. So undergraduates who work with me, they end up making tutorials, so Python tutorials, and I've found that that's quite helpful. So anyone in the room, it's a growing repository, and I'm really happy to add to it, whether you're at the faculty level, but having your students. The idea for me was having a capstone project of like, I learned this skill. And so making a Python notebook that teaches that skill, it might be, okay, how do you cross-match catalogs? How do I can't think of other ones off the top. How do I read in catalogs and do this? Just pretty basic astronomy-related skills, but having a place that students can look to see examples and get help. And so if anyone there wants to contribute, please.
It's wonderful. Thank you. Let's talk a little bit more. I will finish now this event of the seminar, so we can talk a little bit more about this who are interested. Also, if you have some minutes more after we finish. So before, I would like to thank you again. So let's thank you, Catherine, again for the talk.
Thank you so much for having me.
Thank you a lot for your time, your knowledge, and thank you, Richards, for all the supports. And yes, I think we can finish broadcast. If Katarina wants to say something to finish here, otherwise we can.
I just thank you so much for having me. I mean, this is such a great experience, and you all bring to the table your own experiences. So whether it's related to outreach or research or wanting to get involved with some of our treasury programs, I'm super happy if you want to reach out at any point. It's great to make connections, so thank you.
Thank you. So Richard, let's stop the broadcast, and also everyone feel free if you want to